what I do want to talk about today is work that I've done over the past, 10 years or so, kind of expanding what we do with zircon, but adding other accessory minerals to it, so a multi-mineral approach. And a lot of the stuff we've been doing is looking at Archean crustal evolution. So my examples are going to be from the Archean. I'll tell you right now, I've not been to a lot of these places, so it sounds better than it actually is. So I'll give you guys a brief outline because I'm going to talk a fair bit about isotopes and geochronology. So just for some of you who need a little bit of a refresher, I'll do that. But I'll talk about the accessory minerals that are going to be in this study. I want to put everything into the context of this so-called hafnium-neodymium paradox, and I'll explain what that is. I'll give kind of a primer on samarium, neodymium, and lutetium hafnium isotope systematics just for what we need to get through this talk. Hopefully this doesn't put everyone to sleep. I'll talk a little bit about the general zircon and hafnium whole rock records from the Archean, and then I'm going to focus on some examples that we've studied in detail, which is the Acasta Gneiss complex, the Minnesota River Valley, and the Pilbara here in Australia. So a bit of this work is mine. So the data from Acasta is something that I did about 3-4 years ago, but I'm also going to present some work from former students. A few of you may have met Ross Salerno. He was visiting and just up in the Pilbara doing some field work. So I'm going to introduce some data that he's collected from the Mount Edgar complex. And then another student currently just finished at the DTM, Da Wang, who's done some work with those guys and us here at UWA, looking at the Minnesota River Valley gneisses, which used to be, some of the people used to think those were the oldest rocks on Earth. But they're only 3.5, so not too bad. So all of these studies kind of focus on zircon. That's like the benchmark. That's how we know a lot about Archean crustal evolution. But we've also started looking at apatite, titanite, and allanite, which host another isotope system, samarium neodymium isotopes. All right. So a lot of what we know, as many people here in this room understand, comes from the mineral zircon. And for those of you who aren't familiar, the reason that geologists like it so much is that it's by far the best uranium-lead geochronometer. It gives you the most precise ages. It doesn't have any common lead, which complicates analyses. It also contains, oftentimes a weight percent of hafnium. And so because of this, we can measure the hafnium isotope composition in zircon at really fine scales, kind of almost to the level of spatial resolution we can do with a shrimp or with a modern laser system. Of course, there's oxygen isotopes. And very importantly for zircon, it's durable in a lot of geologic environments. So sedimentary transport, it survives magmatic episodes. So this is a sample of a Jack Hill zircon, a rather famous picture from John Valley. And just to give an example of the power of zircon, in 2001, people like Simon Wilde and Stephen Moy just looked at the oxygen isotope composition of zircon. And they noted that it suggested the existence of very early continental crust 4.4 billion years ago, but also liquid water at the Earth's surface. So zircon, without a doubt, is a super powerful mineral for geochemists. But so, like I said, what I want to talk about is what can some of these other accessory minerals like titanite and apatite tell us about crustal evolution, and maybe how can they complement the zircon record. So the two minerals I'm going to focus on most are apatite and titanite. Apatite is a calcium phosphate, which also contains some volatiles. Titanite is a relatively common calcium titanium silicate. Apatite occurs in most igneous rocks, and it's really useful because it's in a lot of rocks where zircon is absent. So it is a useful way. It's difficult to date, as I'll tell you, but it's so ubiquitous that it's becoming a very popular mineral to investigate. Titanite, on the other hand, is in the igneous realm is kind of limited to more metaluminous igneous rocks. Both of them occur in metamorphic rocks, which somewhat complicates their application. but it's also can be used. We can also take advantage of it as well. Both of them can be dated, and I know Craton's doing a lot of this, we're doing a lot of this. It is more difficult to date than zircon because it contains common lead, and you will see the effects of this later. And what it means is just you get a less precise age, but extremely useful, and it oftentimes tells a different story. And that's because it has a different, these minerals have different closure temperatures relative to zircons in terms of their diffusion, to their, the closure temperature to lead diffusion. And one of the things I'm really going to highlight here quite a bit is that both of these minerals contain, or can contain, fairly significant neodymium contents, which means we can measure their isotopes in situ, the same way we can measure hafnium and zircon in situ. And then the other mineral that I'm going to just briefly talk about, which is a super cool mineral, but kind of difficult to work with, but I'll show you some examples where we include this in some of our studies. It's a very complicated epidote group mineral. It's present in metaluminous rocks, often the same rocks that have titanium or titanite can have allanite. It's also in metamorphic rocks. What's interesting about it is it contains ridiculous amounts of neodymium isotopes. So it has more neodymium than a zircon has hafnium, up to 4 weight% sometimes. And it also has very low samarium neodymium ratios, which means getting back to the initial isotope values, which is something that we're striving to do in the Archean. It does make it a little bit easier. We can date it, but because it has so much samarium, things like uranium, but especially thorium, it's very, very difficult to date unless it's really young, because it's just very much radiation damaged. So what I want to do is talk about how all zircon, apatite, titanite, allanite, all of these can address what's called the early Earth hafnium neodymium paradox. And so what is that? That's really that to a first approximation, hafnium and neodymium isotopes are correlated in the geologic record, but not so much in the early Earth, and that's what I'm going to talk about here, and the reasons why. So this is a plot of what's called the hafnium neodymium terrestrial array, and so this is a plot of the epsilon hafnium value versus epsilon neodymium, and what you can see is that these two isotope systems are fairly well correlated. I mean, this covers a huge range of different rock types. The only real exception to this is this seawater array, which is determined from manganese nodules at the ocean floor. But the paradox comes in that this isn't really true in many of the Earth's oldest rocks. So this is a very famous sample. Some people here in this room, I think, even have worked on this. It's one of the oldest original discoveries in Greenland. It's sample 11099. And again, this is the same plot, hafnium versus neodymium. These are all the different analyses, some from zircon, some from whole rocks. And the point that I want to make here, and that Hammerly has made, is that these analyses don't fall along this predicted array. And what we see, importantly, is that there's a much bigger spread in the neodymium isotope composition. So this is something like 8 units relative to hafnium, which is only bearing by maybe 3 or 4 epsilon units, all in the same material, all in the same sample. Some of it's whole rock, some of it's zircon, but there is this huge range, and we're kind of trying to understand how you can get something like this and why it would fall off the array. So to investigate this, I'm going to focus on rocks from the Acasta Gneiss, where we have data, the Minnesota River Valley, and the Pilbara Craton, but I'm also going to add some data from the Capfall Craton in southern Africa, and the famous Acasta Gneiss, where that last sample came from in southern West Greenland. So now this is going to be the boring part for those of you who know anything about it, and even if you don't. So I'm going to give you just the very basics that you need to know for this talk for understanding samarium, neodymium, and lutetium hafnium isotope systematics. So the idea in a very broad sense is that when we partially melt the mantle, we produced an enriched crust, shown here, and we also produce a residue from this, and that's the complementary bit of it, and that's the depleted mantle, which sort of exists in, above the 670 kilometer discontinuity. And the reason that we know a lot of this actually comes from the isotope systems that I'm going to talk about. So one of them is going to be the decay of 147 to 144 neodymium, and this leads to changes in the 143, 144 neodymium ratio, and then 176 lutetium decays to 176 hafnium, and this leads to changes in the hafnium isotope ratio. And these have very long half-lives, 106 billion years for the samarium neodymium system, and 35 billion years for lutetium hafnium. So, like I said, the partial melting of the mantle, so of the depleted mantle, so then this pink part, that leads to a crust that's enriched in hafnium and neodymium. And so this means that the crust generally has lower lutetium hafnium ratios and lower samarium neodymium ratios relative to Chur, which is ultimately going to be our reference frame. And then the complementary depleted mantle has higher lutetium hafnium and samarium neodymium than Chur. So that's kind of these rare earth normalized diagrams here. But the main point is these two systems, the parents and the daughters, behave the same. And this leads to this coupled isotope system behavior, which is why we have the correlation between neodymium isotopes and hafnium isotopes. So, almost done with this bit. So the depleted mantle, like I said, it has higher lutetium hafnium than Chur. So that's this line here. So over the same period of time, it's going to evolve to more radiogenic or higher 143 or higher 176 hafnium ratios relative to their stable ratio. The crust is going to evolve more slowly, so it's going to end up at lower ratios. And then Chur, or the primitive mantle, which we estimate from Chur, which is chondritic meteorites, is kind of our reference frame here, and that lies in the middle. And in order to make this easy, and this is really the important part, is that we're going to turn all of this stuff into epsilon values. And all those is the deviation in parts per 10,000 relative to our reference frame, which is Chur. And so that means over time, the depleted mantle is going to have positive values, and the crust is going to have negative values. This is the main thing that the non-experts need to understand for this talk. So positive values mean generally that the material that you're looking at is derived from the mantle, whereas the negative values mean that that crust is primarily derived from pre-existing crustal materials. Okay, so, and we can see this pretty clearly in the Zircon isotope record. So this is a global compilation from Belousova of hafnium isotopes and detrital zircon through time. Australia, I think, is here in green. It's very well representative. But what we see here are these trends. So we do see this trend for evolved crust, which we know because it has negative values, so we can assume it's evolved crust. And we also have a trend towards the depleted, involvement of a depleted mantle. And that's denoted by these positive values. And all of these things started out at the very beginning of Earth's history at a value 0 relative to the meteorites, relative to the primitive mantle. And we'll talk a little bit more about where this may have started. But so getting back to this hafnium-neodymium paradox, it's been noted for some time, and many people have offered explanations for this. The first one that I'll talk about, but not really focus on, is the idea that the Earth actually has a non-chondritic samarium-neodymium isotope composition. And so some people have suggested that chondrites are actually not the best representative we have of the primordial primitive mantle. Other people have suggested that these two systems become decoupled by the mineral calcium perovskite, and there is some possibilities to this because it's a deeper melting phase. It occurs deeper in the mantle, and people have made some convincing arguments about this. But the part that what I really want to talk about is evidence for this third explanation, and that is that the samarium, neodymium, and lutetium hafnium isotope systems are decoupled by post-crystallization processes. And this means things like, metamorphism, basically, any kind of tectonism. So if we look at the Archean bulk rock neodymium record, and it's important to mention that the data I present for neodymiums is coming from whole rocks, and these are more easily disturbed than the hafnium record, which comes from zircon. But this is what we have for the neodymium record. It's always coming from whole rocks. And so this is a plot of epsilon neodymium versus age. There's Chur. We're going to look at samples here from the Acasta Gneiss in Greenland, the Capval Craton, South Africa, and then the oldest zircon-bearing rocks, Acasta. And what we can see is in that each of these places, there's both highly positive, especially for this age, this is very early in Earth's history. They have both highly positive and negative values in all of these localities. And what this suggests is that there had to be a depleted mantle to get very early in Earth's history to have had enough radiogenic ingrowth to produce these positive values. But at the same time, we had to have a fair amount of enriched crust that also had to form prior to 4.4 billion years in order to get these negative values. So the point being is that this variability is present in a lot of very famous Eoarchean localities, some of the best studied ones on Earth. The zircon record is actually quite different. And this is showing data from extra localities, but also the same one. And what I want to kind of have you focus on is there's a lot of rocks that are within just a few so in the Paleoarchean, Eoarchean, a lot of the rocks here are chondritic. With the one exception is Acasta. And the idea at Acasta is it truly is older crust. And it probably has, originally formed from a chondritic source at, say, 4.2, evolved down. But it never, so it stays enriched. It doesn't have any positive values. And nor does Greenland. All of these values stay chondritic. And so the hafnium record actually shows no evidence of a depleted mantle, while as the neodymium record does show this. And the point being that if we look at the whole rocks and the hafnium, and this paradox is present in just about every Eoarchean terrain. And so people are trying to understand how can this be, and I've given you some of the possibilities. So next I'm just going to go through the evidence that we've collected that I kind of want to highlight here. So the first place that we started working in was with Annie Bauer and Sam Bowering in the Acasta Gneiss complex, which is located in the northwest Canada. So this is like the Coronation Coast. This is the very top end of Canada. So the Acasta Gneiss complex is this little arm right here, and it's located on the western edge of the Archean slave Craton. And very importantly, it's caught up with, it's actually a structural window within the Wopmay orogeny, and this orogeny is going to become important for the rest of our talk. Another thing I want to point out is actually a lot of these samples are collected on just along a river. It's a very small place that these rocks actually occur. It's not the greatest rock record, but it's fascinating to me because it's truly the oldest zircon-bearing rocks on Earth, the oldest ones being 4 billion years old. And I'll show you some evidence for that. So if we kind of zoom in on just the hafnium-neodymium paradox for the Acasta Gneiss, first I'll show you the zircon record. So again, we plot epsilon hafnium values over time. So here's older to younger. And what we see is that there is significant involvement, like I said, for evolved crust. There had to be some pre-existing crust in order to make these new rocks whose zircons we measure. That's it. But at the same time, there's absolutely no evidence for a role of a depleted mantle. And as you'll see, that's not the case, again, in neodymium. This is kind of just a rehash of another plot I had showed you. So with the neodymium isotope record, you can see that there's quite a bit of variability. And there's positive values, so that means we had to have a depleted mantle. And some of those values are actually quite high, and it's led some researchers to talk about this idea of an early, ultra depleted mantle or highly depleted mantle. And then again, at the same time, it does show the same evidence that the zircon record shows, with some evolved crust being part of the new generations of rocks. So Acasta is probably one of the best examples for this paradox existing on Earth. So because these rocks are so old, they've been the source of study since their discovery. Very, very kind of contentious studies back and forth, reviews and comments within journals. Quite interesting, in my opinion. So these authors, Stephen Morbeth is actually the person who he's one of the people who discovered the oldest rocks in Ishua, so he obviously had a bone to pick with these people because he just lost the argument for the world's oldest rocks. But what they did is they did a bunch of whole rock analyses in Acasta, and what they found is that all of the samples that they looked at and the pre-existing samples from the original people who discovered it, they don't show any evidence of this Eoarchean antiquity. They all plotted along this isochron. Now, the isochron has a rather large MSWD, but this isochron gave an age of 3.37, so say 3.4. And if you remember, like I said, there's 4 billion-year-old rocks in Acasta. So this is drastically younger. And so what these guys suggested is an alternative idea for why we see this big neodymium isotope variability in Acasta. And at that time, there were no hafnium data. Neodymium was the way that we looked at these rocks. And so their idea was that, and some of these rocks are granulite grade, they proposed that there was a very high grade event in Acasta, in this small area of Acasta, and that ended up homogenizing the entire neodymium isotope system across the Acasta Gneiss. So during that time of homogenization, all these rocks sort of kind of plotted on a straight line, and then that line, in a sense, kind of rotated up to the age that we measure today. But their contention was that a lot of the neodymium values that we calculate from these rocks are spurious, or at least variable. And the reason for that is because the samarium neodymium was reset, but they calculated those neodymium values at the wrong age. And so that made all this analytical artifacts, and you ended up with this very big record of neodymium isotope variability. Like I said, so I pointed out the importance of the Wopmay origin, of which is surrounding the Acasta Gneiss complex, and this really strongly affected some of the systematics in the Acasta Gneiss, which is, at this scale, it's still just this little feature right there. So to get some idea of the timing constraints on the Wopmay orogeny, the authors that made the last map, St. Ange and Davis, they did high precision monazite geochronology using the TIMS method. So these are very high precision ages. And what they found was that all the monazite ages across the Wopmay origin had a really restricted age range of 1.88 to 1.86 billion years. And so this is 2 billion years younger than the oldest rocks we see at Acasta. And it's also 1.5 billion years younger than that whole rock resetting that we saw in the neodymium isotopes. And what the important point here for what I'm trying to convince you guys of is that this is just super clear evidence that there's multiple episodes of metamorphism at Acasta. It's not a simple place by any means. So I'll get in, now next I want to show you guys some of the data that we've collected in these studies. And all of this data was collected using this method called laser ablation, inductively coupled plasma mass spectrometry. It's something we do a lot at UWA and Craton. And what it is, it's an in situ method where a laser beam samples at fairly high resolution minerals. It creates an aerosol of sample, that sample is then directed into a mass spectrometer for isotope measurement. So this is a shot of the lab for measuring uranium lead at UWA. So the sample is in this laser cell. It's transported into this mass spectrometer. Now, it's not actually hooked up at the time I took this video, but ideally this tube would go back into that plasma torch there, and the detectors are sitting at the end of the instrument. And so this is how we can measure ages. But because some of these minerals are complex, we actually apply a different method. Again, this is something that we're developing right now at UWA, but it's something Craton's been doing for quite some time. And so instead of the traditional way of measuring this stuff where we measure the uranium lead age and then go back on another day in another session, and then we measure the hafnium isotopes. But this can effectively decouple the system because the analytical volumes are quite different between the two methods. And this has produced a lot of problems, especially, for example, in the understanding of the Jack Hills. But in this method, all we do, and it's actually quite simple, is instead of just going to one instrument, once the sample leaves the laser cell, it's split into two different streams, with a portion of the stream, in this case, going to measure uranium lead on this instrument that's kind of ideally situated and designed for uranium lead measurements. And then the other one goes, in this case, to a multi-collector ICP-MS, which offers much more precise values. And this is where we measure things like neodymium isotopes and hafnium isotopes, where we need to get into the 5th, 6th decimal. This is a super powerful technique when it works. It can be very difficult to work with old zircons because sometimes you need a small spot. But in many cases, you can make it work. And what it does is allows you to couple these two isotope systems precisely, because you're effectively measuring them all in the same volume. Okay, so I'll give you some examples of some data that we've collected from Acasta. So this is just an example of what zircon data from Acasta looks like, for those of you who have seen a lot of zircon data. They almost always have lead loss. So oftentimes we calculate intercept ages. There's also ancient lead loss that really complicates things. So these are a bit cleaned up, but we see these intercept ages, 3.91 billion years old. This is super old. This one's 3.7, more lead loss, 3.37. The point being, I just want to remind everyone that these are the oldest rocks on Earth, and their record spans from 4 billion to 2.9 billion years old. But the study and the data that I'm going to show you, we just focused on samples that are greater than 3.35, so they predate that resetting, or we hope it's the best that we have to try to predate that resetting event that we saw in the whole rock record. Now, if we look at a split stream example, so this is the same one that I showed you. So while we measured these uranium lead compositions, we came up with an age of 3.9. At the same time, we measured the hafnium isotope composition in that same analytical volume. We get a value of minus 3.1. And if you guys remember, those minus values mean they have a crustal origin. And so, yes, there was some enriched crust at that time at 3.9. And that goes back to saying the source of these rocks, the precursor of these rocks, in order to get down to 3.1 at this age, they had to probably have formed in the Hadean. But there's no real surprise here. It's just an example. A lot of previous studies have noticed these negative values. So the main points, though, that I want to emphasize here is that for in comparison to other data for the rest of this study, we assume that zircon provides the very best estimate of the magmatic crystallization age. And it also provides the best evidence of primary isotope compositions, and in this case, hafnium. But like I said, we're going to use the zircon to kind of provide a benchmark for better understanding the samarium isotope systematics of apatite and titanite, which I'll get into now. And this is sort of the newer bit of science that I'm presenting here. So we'll start with apatite. So these were determined concurrently using the split stream method. And with apatite, because they have common lead, they don't plot on Concordia, but we can calculate their age by regressing a line through the data and taking the age as the lower intercept. And so we looked at 5 or 6 samples, I think. I'm just showing you 4 of them. And all of the apatite came back with ages from 1.85 to 1.77 GA. So these were reformed, or formed, reset, regrown, whatever, during the Wopmay origin. All these samples have zircon ages that are much older, but they show no evidence of being Archean apatites. And this isn't surprising, given that they could be metamorphosed. I mean, they are metamorphosed. So at the same time, we measure the samarium-neodymium isotope composition. And what we can see is, so this is a typical isocron diagram, just like the one I showed you for the whole rocks at Acasta. What we can see is that most of the apatite, with the exception of maybe this sample and this sample, actually plot on what I'm terming here the Wopmay isocron. So this line has a slope that's equal to 1.9 approximately GA. So the apatite, both the uranium lead was reset or it was regrown during the Wopmay. The other interesting thing is that if you were to calculate those initial values, they project back to a value that's here, at the origin. And this is way more radiogenic than the whole rock array, which plots down here. And basically, again, like I said, this really directly, regardless of whether these are regrown or they're new growth or reset minerals, they're directly documenting the movement of the samarium isotope system during this orogeny. We can also look at the Titanite data from these exact same samples. I'm just showing you one sample here. So the zircon in this sample gave an age of 3.7 GA, 3.373. Titanite in the exact same sample gave an age of about 3.2. So what we're seeing with the Titanite is it's actually younger than the zircon, but it's older than the apatite. So there's 3 different minerals giving 3 different ages. And so this is just additional evidence for how complex and reworked the Acasta really is. It's a very complicated geologic history. If we look at the Titanite from Acasta, I'm plotting it here along with the whole rocks from that Morbath study and a bunch of new ones. There's probably about 60 samples here. The little black dots, which I know, I'm sorry, they're hard to see. The Titanites are in the colored symbols. But what we can see is that there's really good overlap between these whole rocks and the Titanite. So like I said, the Titanite, it overlaps the bulk rock array, but it wasn't affected by the origin. Otherwise, we would see this Titanite starting to try to work its way onto this isocron. And so again, this documents further evidence of that resetting that we saw in the whole rock record, just by simply ablating something for 2 minutes, which took somebody else quite a lot longer to measure. So I just give a quick summary here of Acasta. So zircon has the oldest uranium lead ages. It's recording the magmatic history. The hafnium isotopes also record the primary magmatic signatures. So what we can kind of summarize from this, and this is no secret, is that zircon is by far the most retentive of any of these minerals for isotope systems. Apatite, on the other hand, records just the 1.87 GA Wopmay orogeny, which is younger than the zircon, and the samarium neodymium isotopes are also consistent with this resetting. So apatite in these very old Eoarchean rocks has been completely reset or regrown at a much, much younger age. Titanite is sort of intermediate. Its age is young, 3.35, younger than the zircon, older than the apatite. And again, it's consistent with this bulk rock record that was seen a long time ago. And so the main points here is that in the Acasta, we remobilized samarium neodymium isotopes at least two different times. And we suggest that, the hafnium neodymium paradox, at least in the Acasta, that decoupling between the neodymium and hafnium isotope system happened during these post-crystallization events. So I'll quickly go through the last two examples that I have, but I think these are kind of cool. So the first one is the Minnesota River Valley gneiss. So this, again, is work that's very recent from Da Wang. And these are located in the state of Minnesota, as you might have guessed, very near my home. So I have a little fondness to them. What I want to point out is they show the exact same thing as Acasta. The only thing is they're just 400 million years younger. So we see the neodymium record, again, has this huge spread of 8 epsilon units, whereas the same samples analyzed for zircon are mostly chondritic. There's one point that's a little bit more negative at -5, but you have an 8 epsilon unit spread here, which should translate, if real, to actually what is a 16 epsilon unit spread, or 15 epsilon, 14 epsilon unit spread in hafnium. So these hafnium values are coming out very precisely, whereas you get this giant spread in neodymium, and they should be in really good agreement based on our understanding of the systematics of lutetium, hafnium, and samarium neodymium. And again, very importantly, so yeah, you got the positive and negative values. And again, there's just no evidence for a depleted mantle here. Otherwise, we would see some positive values here. So I'll quickly go through 2 samples just to show you what the addition of these other accessory minerals is recording. So I'm not showing the data here, but the zircon age is about 3.5 GA. Apatite and Titanite in the same sample using the same system, uranium lead, both give intercept ages around 2.6 GA. And that's the timing of a local orogeny there called the Sacred Heart orogeny. The samarium neodymium age that we get from the apatite and titanite, and the whole rock in this case, gives an age about 2.66, which also coincides with the Sacred Heart orogenies. So, and then you can see it here, the apatite and titanite, here's the whole rock. It forms a beautiful isochron here. So, we've completely reset the apatite, titanite, uranium lead, and samarium neodymium systematics here. And so this is just more evidence of post-crystallization modification of these isotope systems. Whether or not they're fully open systems is a matter of debate, but at least we know that we're moving these things around. And it explains potentially why neodymium is so variable and hafnium is much more robust, because it's armored in this mineral zircon oftentimes. And this is another actually interesting sample. So we see the same thing, much older zircon age. We got the titanite resetting to the Sacred Heart origin at 2.6. But interestingly, the apatite records even a different age, so a third age in the sample of about 1.89, which is exactly the age of the Pinokian orogeny, which is another orogeny in that region. And then the samarium neodymium age, which includes titanite, apatite, the whole rock, and a little bit of allanite down here. And this is actually interesting. It's actually giving a much older slope. But even if we include it in this regression, we still are recording in the samarium neodymium system the Sacred Heart orogeny. And what's actually really cool is we've actually decoupled apatite, because the apatite is going to give you a 2.6 GA samarium neodymium age, but even a different uranium lead age. So this is ultimately very informative about seeing like the history of the events that affect these areas just from one rock. And then the last place I'm going to talk about is one everyone here I'm sure is familiar with, the Pilbara. And the reason that we look at the Pilbara is because, unlike Acasta, and kind of with the exception of these greenstone belts around the domes, the Pilbara hasn't undergone these high-grade metamorphic events that the Minnesota River gneiss has. They never reached granulite grade. And so it seemed like a good area to try to compare what we've been doing in the Minnesota River Valley with what we've been doing, or the Minnesota River Valley in Acasta. And so what we end up seeing here, so we focused on the Mount Edgar Dome, and we focused on 6 samples that were kind of collected along a traverse, hitting all of the different suites within the Pilbara, within the Mount Edgar complex. The zircon For these 6 samples, it does show lead loss, but this is quite, modern day, easy to understand lead loss in a lot of these samples. They have really consistent 207, 206 ages, so relatively simple uranium-lead systematics, especially for super old rocks like this. And the samples that we worked on had an age range of 3.47 to 3.39. So that covers a lot of the history of this, this dome. We measured the hafnium isotopes, of course. This was done concurrently. They have really simple lutetium systematics. I mean, they're all more or less in agreement with one another. And what's important here is that the hafnium isotopes in these zircons are chondritic. And, well, broadly chondritic. They're from 0 to about +1. And some other studies might get values of -1, but there's not showing this big spread like we see in neodymium isotopes. In all of these samples, we found titanite, and the titanite actually has relatively simple uranium-lead systematics for titanite. You do see some of these values kind of going up older than the zircon ages, but these ones all have elevated common lead, and what you're seeing here is just the effect of common lead. So the age that we take is the average of these gray points, and then in light gray, that's the age. And those ages are consistent with the zircon ages in the same sample, which means that the titanite has not been reset like we saw it reset in Acasta and in the Minnesota River Valley. And this has to do with, I think, the relatively undeformed nature of the Pilbara. And of course we measured the samarium neodymium isotopes in all of this, and so these include apatite, sometimes allanite, and the whole rocks. And you can see these all make fairly well-regressed isochrons. The airs are somewhat big sometimes, but this is actually quite good because some of these are around 1% or something like that, which isn't bad for laser data. But the ages from these isochrons also agree with the titanite uranium-lead ages and the zircon uranium-lead ages. And it are also consistent with the bulk rock, which we can see because the bulk rock is actually lying on this isochron. So like the hafnium and zircon, these initial neodymium isotope compositions are chondritic, so they're in agreement then. The neodymium and the neodymium and the hafnium are both in agreement, and they're both chondritic. So there is no decoupling of the isotope systems here like we saw in the other 2 locations. This can be a bit easier to see if we just look at a single sample and we take each analysis and correct it to its initial value based on its age. And what we can see is there's really good agreement with the titanite in one sample, the apatite in the same sample, and the whole rock in the same sample. And the epsilon values for these 2 are in quite good agreement with one another. I mean, that's broadly chondritic, which is what I've shown you before. So like I said, in the Pilbara, the hafnium-neodymium system, at least in the Mount Edgar, remain coupled. And that, again, is in contrast to what we're seeing in these poly-metamorphic terranes. So second to last slide here. This is just kind of a global comparison of neodymium, which is based on whole rocks. In this case, these are actually the mineral results, and then hafnium, which is all based on zircon. Again, you can see the starkly different record of these. So, at this age, all of the stuff from Greenland goes positive, whereas here it's all chondritic. But the Pilbara all stays the same in these stars. It's all chondritic. So we can say kind of with a lot of certainty that there is no hafnium-neodymium paradox in the Pilbara Craton. And then just finally to just make a few concluding remarks. So if we compare the Acasta and then as well as Greenland, which I just showed you in the last sample and some of the earlier slides, the Catfall, the Minnesota River Valley, and we compare these with the Pilbara, it gives the impression that the hafnium-neodymium paradox is a result of high-grade metamorphic events that are they're upsetting the neodymium whole rock values while the zircon's preserving the primary signatures. And so some people have argued that this paradox can be explained and it might be a fundamental feature of the early Earth, but it's not necessarily in all cases, I think, is what this data would argue. And then the final thing I would add is by adding these new minerals like apatite and titanite and looking at their uranium lead, but also, you know, the more recently developed samarium neodymium analyses, we can clarify the record of crustal growth and evolution. And in the same rock, we can kind of break out a pretty big history of a number of events, whereas if you just looked at the zircon, we get the crystallization age, but we won't have much understanding of what's happened to those rocks since then. And so I'll just leave it at that. I think that's about it.